Hello, this is Mojam Shidi. I want to apologize for not being in the class live. UTSA started the classes this fall semester 1 week earlier than last year, and I didn't know about it, though I had planned a trip which caused me to miss my first two lectures. However, I am taping these two lectures in July, and one of my colleagues, Dr. Benavides, will also be there present in the class. He will basically give you a good guided tour on some of the projects that we are hoping you will join, because in this semester we eliminated 3 quizzes and we emphasized a course project in the ACE lab in BSE building. I've also added another book, which I will soon give you a copy of it, a book by Professor Phillips and Nagel, and so we'll have 2 textbooks, which I will guide you through topics in either one of those 2 books in due course. So let's go to the book by Franklin and others. But before that, let me walk you through the outline of the course. These are my office location, BSE 1.544. My office telephone is extension 70474, and my office hours is Tuesday and Thursday 2 to 3:30. My preferred email address is mojamshidi4@gmail.com, but you can also send it to UTSA. And as I mentioned, we will have 2 books, Franklin Powell and Workman in 1998, and 1995, Phillips and Nagel. These books, both of them are rather old, but the concepts are really the same as we have it today, except for the speed of the clock in the computers and speed of conversion and sampling rates. We'll go over that later on. Almost all handouts, maybe except with the second book, is already on Dropbox, and we also have emphasized on a lot of MATLAB related homework and project per se. One of my own books for 1986 book will also be on Dropbox, and it's on linear system, a computer-aided approach. And in addition, this website, you can go and download many of my 11 textbooks free of charge. No password is needed. So these are the topics that we're going to be discussing. The course project objective is to demonstrate the knowledge of mathematical representation and properties of discrete time systems, and these are the main approach. And due to the fact that you are going to be spending time in the research lab, you will be working with PhD and master students, and thereby you will be able to actually see the theory in action in the lab. And those projects are going to be the, I think, lasting memory from this course for you, and would help you when you do a job search after graduation. These are the topics we are going to be covering. And I know state space models, you may have not seen it in your senior control class, but in any case, we will cover that, and we will have 2 75-minute lectures per week, and the grading of the course are based on homework, examinations, two midterms, a design project, and final exam, of course, and project presentation. So this will be here are the time for the two midterms, September 27th and November 29th. And on December 7th, we have at AceLab projects, reports, and presentation. Each group will be having 20-25 minutes to present it, and final exam will be 2.5 hours on December 10th. So much for the logistics, and of course, if there's any additional changes, I will keep you posted. And now, looking at this first book, let me go to chapter 1. Okay, as you will see here, this is a typical digital control system. You have an analog plant, like a robot or like a DC motor or maybe an automobile or what have you. And this plant always expects an analog signal coming in and puts out an analog signal going out. The objective is to have some reference input be followed, copied by the output. The output is being censored by some electronic sensors, could be potentiometers for position, and accelerometer for acceleration, pressure sensor, you name it. All these physical quantities, which are in terms of physical quantity, are fed into the sensor, and the sensor could be subject to some kind of disturbance or noise, which we'll talk about it later on in the course. The output of the sensor is going to be some voltage, but that voltage is going to have to still be in analog format. It's going to go to analog to digital conversion unit, and then it will be converted to a digital quantity as a sampled signal. And that will become compared with the sampled reference input. It produces an error, and this error will then go into a digital computer, a microprocessor, or more recently, microcontroller boards, which is run always by clock, and that clock synchronizes analog to digital conversion and another unit called digital to analog converter. So the object of digital to analog converter is to take a digital information in number of bits, convert it to a voltage, which a plant can now accept it. So this is a typical block diagram and architecture for a digital control system. Now, later on you will see a variety of this same block diagram, but the essence is the same. You will basically have all these units in one form or the other. Some of these things could be in the forward path and so forth and so on. Now, in a number of issues that you see in this particular figure, you saw the plant, you saw the fact that you want to match the output to follow the input. That's called regulation. You may have some disturbances. As you see here, you may have disturbances to the plant itself, in addition to error or noise in the sensor. In that case, you have disturbance rejection issue. You need to add additional control architecture, control hardware to reject the disturbance. Now, you may also have face some changes in the plant parameter, and you want to know how those changes are going to affect the overall performance of the system. That concept is called sensitivity. Another issue that may not come very vividly here is you may have a plant changes, plant dynamics change, and the control in the control computer has to still be good enough to do its job in spite of those changes. That's called robustness. So a robust control is a controller which remains essentially viable in the presence of dynamic changes in the plant parameters and so forth. So there are many concepts which I'm not going to bore you with it right now, but we have a sampling period, we have interrupts, free running situation, event-based sampling, discrete signal, which are basically a continuous signal which is available only at quantized discrete formats. A system which has both continuous and discrete signals running around the loop is called sample data system. We also have a concept of quantization, and that is that analog to digital converter provides what's called a quantized signal, which holds the signal between samples so that the analog plant still has some kind of input. It doesn't disappear inside the plant. So we will, in this course, we will basically call the system either digital control or discrete time control. They mean the same thing. And digital signal is also a system which is both discrete and quantized, which will come to it later on. Another concept which you will be exposed is emulation. Emulation is the situation where you look at the analog controller, but you convert it to a discrete format, and you try to then control your system from that new discrete signal. In other words, that design of that discrete control is not directly coming from a discrete plant. You have already learned how to do analog control like PID, PD, lead network, lag network, and so forth. We convert those into discrete equivalents later on. This is a plot of the output of an analog to digital converter versus, let's say, input analog coming in, output discrete going out. Notice that it's sampled at 0, 1, 2, 3, 4, 5, and so forth. And notice also that between the samples, the signal is being held. So it's like a staircase. As you can see, that staircase signal is going to be constantly available in the input of the plant. So we will have a number of design criteria. We will in due course define ripple effect, aliency, and sampling theorem. We're all going to be part of the course. And digital filters are discrete time systems. And what you learn in this course is also very much applicable to a digital filter. And in modern control theory, we will have a state space approach, and we have a transform approach for Laplace or Z transform, and we will have a state space representation of a plant. You will learn a new approach in modern control design called pole placement, or sometimes called eigenvalue assignment. Optimal control, if we get time toward the end of semester, we'll visit that, and I will be happy to define it and present it to you. Identification is another concept which is more advanced topic in chapter 12. Basically, when you have input and output information of a plant whose model is not quite identified for you, you could use system identification approach to come up with a model for that plant, which otherwise would be like a black box. So again, those are also available. In MATLAB, there is a toolbox for system identification toolbox. As far as MATLAB is concerned, we will have you work in the control approaches, in the control toolbox quite a lot, which has both continuous and discrete modules. And we also, depending on your course project, we will get you involved in other toolboxes. I know, for example, even advanced topics like machine learning were covered last fall by some of my students. A lot of times they have heard about the concept. You can come to me and we will tailor a project for you. In addition, those of you who are doing a senior project, we can discuss to see what you are doing in senior project, and the course project could be a subset of your senior project. And you're welcome to work on it inside the ACE lab. So these are basically ideas here. And let me now go to chapter 2, which is a review of continuous control. You're supposed to have basically learned much of this material already, but let me see if you, here is a state space representation. Instead of a differential equation, you have a set of first order, let's say you have an nth order differential equation representing a linear time invariant system. You could represent that differential equation or that particular system by n first order linear differential equation. Equation 2.1 represents n differential equation, x1 dot, x2 dot, all the way to xn dot. And F is the system matrix, n by n, and G is a control input matrix, which is n by m, and U is the number of inputs, could be m, and X is the number of states, which is n by 1, and Y is the output, which is p by 1 output vector, and H is 1 by n. If you have one input, one output, 1 by n, and J here is a scalar value, 1 by 1. In most of the examples in this course, like you saw in your control class, we have one input, one output. Therefore, G would be a vector, H would be a vector, J would be a scalar, only F would be a matrix, n by n. You normally have more than one state. So for a second order differential equation, F will be 2 by 2. So let's look at an example here. Here's a second order differential equation, which is represented by y double dot plus 2 xi omega n y dot plus omega n square y equal k0u. This is a typical model for a second order system, which has a natural frequency omega n, damping ratio of zeta. If we call y as x1 and y dot as x2, then x1 dot is going to be y dot, which is x2. So x1 dot is x2, which is 0 times x1 plus 1 times x2 plus 0 times u. So that is the vector representation of that simple equation, x1 dot equal to x2. Now, when you do the derivative of x2, x2 dot is y double dot. Y double dot is already available. So it's k0u minus omega 0 square y, but y is equal to x1 minus 2 zeta omega n y dot, but y dot is also available as x2. So here you have x2 dot is minus omega n x1 minus 2 zeta omega n x2 plus k0 times u. So now you can see equation 2.4 is a valid representation alternative representation of this second order differential equation. This is called a state space form. Later on, we changed that x dot to a discrete form. So everything will be discrete. Right now, everything here is analog continuous signal. And of course, you could take the Laplace transform of this equation and change it from a differential equation to an algebraic equation. And you could then have an alternative way of solving it by inverting the Laplace transform. So you know that Laplace transform of a derivative of a function is S times transform of that function. So if you take the Laplace transform of that equation, you get this. If you find the ratio of y over u, which is your transfer function, g, you have k0 over this. Now notice from your control class, this denominator is characteristic polynomial. If you set that equal to 0, it will be called characteristic equation. The roots of this characteristic equation are called the poles of the system, which it turns out is identical to the eigenvalues of the matrix F, a system matrix. Now, if you haven't had any linear algebra background, you may need to read a little bit either in the internet or in your appendix of your books on linear algebra, what is eigenvalue, what is eigenvector, and so forth. So in general, you could have a transfer function looking like this. If you want to use MATLAB, you can define a numerator and a denominator, and then you can use the transfer function command in MATLAB, and it will give you a system configuration. And then you could, in fact, use zero and pole and gain using another approach. If you only have basically zeros and poles available in this fashion, you don't have to go through, you don't have a numerical polynomial approach. You only have the location of zeros and poles. MATLAB will allow you to do that also. The answer would be the same. You have a system configuration. So again, here you have basically one approach. SS is the state space format of F, G, and H and J matrices. And you could also have a transfer function of a formulation of in Laplace transform, and through SS, a state space, converted to a F, G, H, and H and J matrices. Okay, and you have signals, a step input, ramp input, parabolic input, sinusoidal input, and so forth. You also remember from control class final value theorem. The final value of any variable as a limit of x of t as t goes to infinity is equal to x steady state, SS, which is in Laplace transform, is limit as s goes to 0 of s times x of s. Okay, and we will have a discrete version of this later on. And block diagram, you're already familiar with this. Input, output, and input, the closed loop transfer function, you're familiar with that. You could look at, for example, response versus pole locations. Depending on the location of the pole, you have different kind of responses. The destiny of performance of a system are directly resulted from the location of the poles of the system. And you may have an open loop pole which is roots of this, or you may have a closed loop pole which is the roots of this characteristic polynomial. So you know that in continuous time system, when the poles, closed loop poles are on the left of the S-plane, the system is unstable. And also, if you have, let's say, a first order system, 1 over S plus sigma, the impulse response, which is the direct Laplace inversion of your open loop response, is e to the minus sigma t times unit step function. And the invert of sigma, 1 over sigma, is called time constant. And if you have more than first order, maybe second order system, which happens to have a pair of complex conjugate poles, you can create a corresponding polynomial whose roots are these poles. So basically create that polynomial as S minus this times S minus the other one. You have a plus or minus here. S plus sigma minus j omega d times S plus sigma plus j omega d. It gives you this polynomial. Sometimes when we do the pole placement or eigenvalue assignment later on, we call this desired polynomial. Okay, let's see, this is the response of that first order system. And notice that when you do a tangent at the point 1 at corresponding to time 0, the location of interception of this tangent and the time axis is called the first time constant. And you can do the same for second time constant, third time constant, and so forth. Normally, after 5 time constants, you reach almost 0, very close to 0. We call that settling time, you recall in your control class. So, again, damping ratio is same, sigma, omega n is natural frequency, sigma is the value of the real part of the pole, and they are shown in here, right here. This is sigma, the real part of the pole, this complex conjugate pole. The distance from the pole to the origin is natural frequency, which means if you draw circles, a number of circles around origin, you will have constant natural frequency. This angle right here, you see here, or this angle, depending on how the cosine of this angle or sine of this angle is equal to zeta. So if you draw an array of a line here, you measure this angle, take the cosine of that, that gives you the value of zeta. And you can write a piece of MATLAB code to come up with your response. That's one thing you could do. And this shows you a sequence of responses for different value of zeta. When zeta is 0, you have sustained oscillation. Your poles lie on the j omega axis. As you increase the value of sigma, you have damping into the picture. The eventual signal will go down. And when you reach to about sigma equal to 0.707, somewhere here, you fall right underneath the line 1, which is your steady state or reference input. And beyond 0.707, 0.8, 0.91, those are called underdamped signal, overdamped signal rather. Those called underdamped signal, and of course zeta is called pure oscillation. And now this figure shows you location of poles and the type of responses you should expect. Here is, for example, a pole on the j omega axis, you have pure oscillation. If you have pole in the right half plane, it blows up. It goes to infinity, either through oscillation, if you have complex conjugate pole. If you have real pole in the right half plane, you're going to have this kind of parabolic, exponentially going to infinity, and you have unstable system. If you have just the origin, you have a neutral situation. It's just going to stay there. It's not going to go to 0. It's not going to blow up. Now on the left-hand side, you have a lot of well-behaved situation. You have a pair of complex conjugate pole. Here you basically decay until you reach a steady state value. If you have real pole in the negative real axis, it will go down, as you saw also before, and so forth and so on. So the location of the poles, as I said, is very, very important. In continuous time system, you have rise time, settling time, overshoot. These are values which are defined here, are part of your specification. And here you have, for example, the time going from 10% to 90% of the signal. This is called rise time. And the value of the maximum first overshoot minus the steady state value divided by steady state value times 100% is called percent overshoot of the system. In general, you don't want to have any overshoot, because if you are reaching a destination, you don't want to miss the target and go beyond destination. If you are cooking food in a rice cooker or some other slow cooker which has some kind of control mechanism, overshoot of cooking means you're going to throw away the food. It's going to be bad. So normally you don't like to have any overshoot. You prefer to go fast and stay close to the steady state value. And as I said before, you have a value called settling time. Settling time is the first time that the signal reaches to plus or minus, let's say, 5% or 3% of the steady state value. That is called settling time. And those values are related to sigma and omega n. Settling time is, say, for 5% criteria, 4.6 divided by sigma or zeta omega n. Rise time is approximately 1.8 over natural frequency. The peak value of the signal, e to the minus pi zeta divided by square root of 1 minus zeta squared. You have to note that these conditions are constrained by the following factors. They have to represent linear time invariant system. It is approximately for a second order system which has only two poles in the left half plane, one here and one here, let's say. Because conjugate poles, as you know, they come in pairs. They don't come by themselves. So if you have two of your many poles are close to j omega axis compared to way back here in some other poles, these two poles are called dominant pole. And those equations are only good for the dominant condition. Remember that. These conditions are only relevant to dominant condition. So let's say if you want to have a 16% overshoot for a zeta 0.5 and then percent overshoot would be 5% is for sigma equal to 0.7. These are shown in this graph. Percent overshoot versus zeta. If you have zeta is 0, that means no damping, means pure oscillation, and you have 100% overshoot. You have sinusoidal situation. It goes up and down plus or minus 100%. If you have let's say 0.7, you have maybe about 5%. If you have 10% overshoot, it's roughly 0.58 zeta. So once you know what percent overshoot you want, you come to find zeta, you move that zeta to the S-plane, you know where you're supposed to end up. That will be your now, here you have a typical design control system. You have a plant, you have sensors, you have compensation, which is like a PID controller, PD controller, and measurement noise, and so forth. And these are typical continuous time control system, which you already have seen it before. You could have a disturbance on the plant, as you saw before. You could have a measurement noise. A steady state error, if you look at this diagram, the response of the system with respect to the error, you see that between R and E, you have nothing there, so it's just 1. But if you go through the loop, you see 1 plus D times G of S, so E of S over R of S is 1 over 1 plus D times G. This is the transfer function of the error. And sometimes we call it sensitivity function. If you have, let's say, you apply the final value theorem, you will see that steady state error is 1 over 1 plus Kp, where Kp is limit as S goes to 0 of D times G. And where Kp is called the position error constant. And it also depends on the type of the system. Type 0 is when you have S to the power of 0 in the denominator. Type 1 means you do have a single S1 multiplied by the rest of it. And type 2 is S to the power of 2. So depending on type 2 and the signal, you have different values of the steady state error. When you have a ramp input, for example, and a first order, first type, you have a velocity constant situation. And you have 1 over kV would be your error. If you have a sort of acceleration input, where you have a second order, let's say a parabola as your desired input, your acceleration constant is limit as S goes to 0 of S squared D times G. This table right here, it shows you types versus types of input, types of plant. If you have type 0 plant, that means you have no S individual isolated S in the denominator. The steady state error is 1 over 1 plus Kp. At the same time, if you put a ramp input into type 0 system, you'll get an infinite error or a parabolic infinite error. So this is the first row of that table. The second row is for type 1. When you have a ramp input and type 1, then you have a finite error 1 over kV, where kV is the velocity constant. And if you have a step input into a type 1 system, you always guaranteed zero response. Sometimes a PI controller, which as you know has an S in the denominator, and that will changes the type of the system from type 0 to type 1, then you will have a 0. If you have a step input, you have 0, guaranteed 0 step, steady state. If you have type 1 and a parabolic input, again you get an infinite error. Finally, type 2 system for parabolic is 1 over Ka, Ka being the acceleration constant, and before that, for ramp and step, you will get 0, guaranteed 0 steady state error. You have also seen PID control signal. Here it is, and you have 3 components: an integral component, proportional component, and a derivative component. And in discrete form, you have this kind of transfer function for your PID controller. Notice that the 2 parameters, TD and T1 or TI are to be defined and to be obtained by a designer. Okay, a lot of times using MATLAB, you could do trial and error and work with TD and TI until you get the desired response. Root locus you are already familiar with, and you have basically parameterized location of the closed loop pole for the gain of the system to be changed from 0 to infinity. So typically the most important thing in the root locus is that the sum of all the angles of the zeros minus the poles must be 180 degrees or plus or minus 180 degrees to be able to satisfy the condition of 1 plus KB over KA. So as you see, if you put 1 on the other side, you get -1. -1 represents an angle of plus or minus 180 degrees. That's why this condition is relevant. Then of course, the magnitude of B over A must be equal to 1, and that gives you the actual value of K as you move from a point to another point on the root locus. So typically, you have these kind of rules, which we don't want you to follow that because you're supposed to already have done it in the control class, but I will actually give you some quick set of rules, not all of them, to get you a ballpark situation about the shape of the root locus. One important thing is that you have nth order system, that means you have n branches. And you have m zeros, that means you have m finite location for zeros. M of those branches are going to end up at these m zeros. The rest of them goes to infinity. And they go to infinity by asymptotic angle, which is obtained by this angle, and the intercept of the asymptotes are going to be hitting the negative real axis at this value, minus all the AIs, minus all the sum of the poles location, minus sum of the zeros. Other issues like departure angle, arrival angle, you don't have to worry about it because the bulk of your practice and your homework, you will be able to, you're all doing it on MATLAB. So, but let's look at this particular system. We have second order polynomial, that means you have 2 branches. And you have a 0 at s equal to 0, and you have 2 poles plus or minus j omega. Here omega is equal to 1. So you have 2 poles at plus or minus j1 and 0 at the origin. Now n minus 1, 2 minus 1, one asymptote is existed and departure angle is 180 degrees because if you look at that, it's going to be basically 2 times 90 degrees, which is what you have here. So the departure angle is going to be obtained by this fashion. It's going to be location of 90 degrees for the first pole, 90 degrees for the second pole, and minus 180 for the 0. You end up with minus 180. And that's going to be this line. Now this is the 2 poles. This is the 0. Now another rule which is you need to remember is that going from right to left of the x-axis, all the segments to the left of odd number of poles plus zeros are going to be part of the root locus. In other words, if you go here, you have 1 0. We don't count that because that's not here. This is part of the root locus. So now you have established here, you need two branches leaving from these two poles, coming toward this line, and they arrive at this point. You can also calculate that the arrival point, and another one comes here. If you have enough line points calculated, you see that it's going to be circular fashion. So one branch comes here, hits the negative real axis, and heads toward the finite zero. The other branch comes here, hits the negative real axis, goes to infinity, as we said before. So this is now root locus of positive k. If your gains are negative, then these are going to be your root locus, going this way to zero for negative values of k. But those are not realistic in a control system, because you have gain of any amplifier cannot be negative. So again, you use root locus if you want to, let's say you have a plant, second order plant looks like a DC motor, and you have let's say a control architecture which may be a lead network. You define your numerator of the D, which is 1 and 3, denominator 1 and 10. You define your plant, the numerator is just 10, the denominator is 1 and 2 and 0, s squared plus 2s plus 0 is this. You create, you multiply a transfer function for the plant and the transfer function of the controller, this like this, you call that sys. That is, this sys is g times d. And then you increase the gain of the system from 1, 0 to 4 at the steps of 0.1. Basically means 4 divided by 0.1 is 40, plus the 1 at 0, you have 41 points. Then those 41 points goes in here to the command for root locus. It's called R locus. You bring the system here, K, and then you will draw the root locus. And here it is. Root locus is drawn here. A pole here, a pole here, pole there, and then in between the two poles you have a break, a waypoint going to infinity here, infinity there. Another branch goes from here directly to 0. And if you plot it on a step response or impulse response, you will get, for example, here is the root locus, and B is the step response of the system. Step 1, as you see here, and you have a maybe settling time of about 1.2 seconds, which is pretty fast. Okay, and then you can calculate from this experiment the value of omega n, which you can obtain from point of 0 to there, right here. That's omega n. And the cosine of this angle here is zeta. There are other ways you can also compute zeta omega n from the original equation. So you calculate peak time, rise time, settling time, maximum overshoot, all of those you can calculate, and it will give you a good understanding of that. Now you can do design using frequency response. You could have your plant, you could have a sinusoidal function with this Laplace transform, and you come up with an output, which also would be a sinusoidal function, except that it has a change in the amplitude, depending on the value of the input signal, U0, and then of course you also have a shift in the frequency. So you'll get two changes. Your amplitude will be original amplitude and the amplitude of the input, and then you have a shift in your frequency of phi. So you pick up a phase and a magnitude in this process. The phase is going to be angle of j omega 1, imaginary divided by real with a tangent inverse or arctangent. That's how you calculate it. And the magnitude of g will be equal to a. And then if you plot magnitude and phase together, here's the magnitude of a various number of second order system for different value of zeta. Notice that for zeta equal to 0, this actually blows up, goes to infinity. 0.05 it goes to about 10. It peaks at 10 and comes down here toward the end. Here is going to go down minus 40 dB per decade, meaning going from 1 to 10, you go from, let's say, 0 to minus 40 dB. This is decibel. So depending on the number of poles in the system, each pole contributes minus 20 dB. So if you have second order system, your final frequency response, we call that body plot, magnitude of body plot, will be has a slope of minus 40 dB per decade. And you also have the phase diagram. A combination of this diagram and the one previously is called body plot. And this is the phase value. And as you can see, if you have two poles, you're going to be 2 times minus 90. You end up at minus 180 degrees. Okay? And if you have only one pole, you end up at minus 90. And if you have 3 poles, you're going to end up at minus somewhere down here, minus 270, 3 times minus 90. So remember now, every pole has a contribution of minus 20 dB per decade in the magnitude part, and it also has a contribution of minus 90 degree phase in the phase plot of the body plot. And you can, here, for example, remember the body plot, and you have here angle of 1 plus j omega 10, which basically starts at one break point here, and then it has a second break point here, which approaches toward asymptote up to plus 90 degree. Because 1 plus j omega is 1 plus s is representation of a 0. For a 0, you just have the opposite. For every 0, you're going to have a plus 20 dB per decade contribution in the magnitude plot, and in the phase plot, you will have a plus 90 degrees for every pole of the 0, or rather every 0 of the system. So that's the situation there. Now, in control class, you notice that you have some stability margins. Stability margins are phase margin and gain margin. Gain margin is the factor by which you could increase the gain of the system at the present location before it becomes unstable. Or you can have a factor so that if it's unstable, you can reduce the gain to make it stable. And if it is larger than that factor, it becomes stable, the poles move to the left half plane. If it is just equal to the value of, let's say, gain margin, it becomes pure oscillation. The phase margin is the additional angle which you can, positive angle, you can add to the system's phase before it becomes negative, okay? And for that same second order dominant pole situation, an approximate relationship has been established between damping ratio and phase margin divided by 100. So these equations are going to be handy later on when you want to do design in the frequency response. Okay, so we have about 15 more minutes left in this lecture, and in frequency response, you can also do a design. Suppose you're given a analog plant here. You want to find the phase margin and gain margin of the system, and with a unity feedback, where we have a gain k equal to 1, and we want to also find out if the system is stable if you increase the value of k from 1 to 5. And finally find for what value of k is required to achieve phase margin of 45 degrees or 70 degrees. In this situation, as long as phase margin is positive, your system will be stable. That means you can afford additional 45 degrees of negative phase before the system becomes oscillatory. And we can do all of that on MATLAB. For example, you define the plant, you define your system, and you define the body plot using the body plot here. And you can go and read the phase margin from figure 2.15, and this is right 2.15 here, 15. So this is the gain or the magnitude plot of that system. This is the phase plot. Notice that you have 3 poles here. Look at here. You have 2 plus 1, 3 poles. As I just said a few minutes ago, when you have 3 poles, that means you end up with minus 270 degrees phase. And that's what you happen here. Minus 270 degrees phase. And your end plot for the magnitude will have a slope of minus 60 dB per decade. That's how fast that magnitude plot goes down. So because you have 3 poles, each of them minus 9 degree and minus 20 dB, 3 times minus 20 gives you minus 60 dB per decade at the end. Now, in order for you to find the gain margin, you go to the magnitude plot, you find out at what point it's going to hit the 0 dB or the magnitude 1 line. Remember, log of 1 is equal to 0, okay? This is logarithmic scale here. So you come here down with the 0 dB point, keep that frequency intact, then you can come here and say you're going to hit it here, and from here to here you have 22 degrees left before you run out of phase here. This phase right here is 0. Here is 22 degrees. So the system is stable. 22 is a positive number, and you have a phase margin of positive 22. At the same time, you hit the minus 180 line. This frequency, you go up here, and you see when you hit here, this distance is going to be 6 dB. So you still have positive gain, positive dB. Your system is stable, and 1 over GM is 0.5, meaning that if you if you multiply the gain by 0.5, you will basically run into problem. So that is basically having your pole in the root locus go from left half plane, hitting the j omega axis, and go to the right half plane. So in body plot responses, analysis, and design, you want positive phase margin. Okay. And then the rest of this problem, figure 2.16 shows the system is unstable for k equal to 5. 2.16, let's say, here is, you have at the gain of 5, you come down here and you have 70 degrees phase margin. Okay. Now, if you increase the value by, if you keep increasing the gain of the system, you reduce the phase margin. It becomes 45 degrees for k equal to 0.5, and now you keep increasing it to, let's say, 5. By the time you reach 5, you have gone beyond minus 180 degrees. You are approaching toward minus 270. This will give you a situation where you have a negative phase gain margin. That means you have to reduce the gain from 5 to at least 1 to be able to revive the stability of the system. So in this situation, you will have, as long as you have a negative phase margin, your system is unstable. And as long as your gain margin is less than 1, you have unstable situation. Meaning that the gain of the system has to be reduced by the factor of gain margin to bring it into the stability region. And same situation can be done for the Nyquist plot, which we will discuss later on in the course. In the state space approach, where you may have multi-input, multi-output situation, we later on help you understand what's the concept of observer or estimator, and we also show you what we call pole placement problem. We have your control is minus a gain times the state variable. K1 through Kn are unknown, and they are obtained by a command in MATLAB called pole placement. However, in many cases, the number of the state variables coming out of the plant, which are measured by the output, this output is less than n. So you need, if you have a state feedback, you need to find an estimator, additional hardware, using the input and the error of the output, combine them to give you estimated state. And that is going to give you some kind of observer. We sometimes call it Leuenberger observer, after Professor Leuenberger at Stanford came up with that in the 60s. And then pole placement is going to be done here. When you close the loop, you have the gain K coming into here, and you want to get a set of desired poles for your pole placement. Your poles may be in the right half plane, you want to move them in the left half plane. So you come up with a desired characteristic equation. Remember, we talked about S minus sigma plus j omega times S minus sigma minus j omega multiplied together. This is a more general representation of creating a polynomial whose roots are your desired poles. Okay? And there are another concept of controllability, which means under what condition K can be obtained. or observability. Here, by the way, are the two commands in MATLAB, Ackermann equation, which are described to you later on, and placement, pole placement. You use the system matrices and rotation of desired poles. It gives you the gain. Same here, same there. You will use that later on in your problem. This is the optimal control, which again we may or may not get to it at the end of semester, and we will use the criteria, a cost function to be minimized at the same time that you obtain the unknown gain matrix K for the controller. You also optimize something. You minimize the cost. You maximize, let's say, profit, and so forth and so on. The LQR is the command for that in MATLAB. Linear system, quadratic cost function, and regulation. Remember the word regulation I mentioned at the beginning of the lecture. So again, these are when you have a transfer function like this, 1 over s squared, you can represent it by a differential equation and write the state equation, and it will actually give you a F matrix and G matrix like this. And you can do it all in MATLAB. And you can use linear quadratic optimal control in MATLAB. And EIG is the eigenvalue command in MATLAB. Anytime you want to find the eigenvalue of any matrix, it will give it to you. Okay, so this is going to be the first lecture, and as I mentioned to you, this is your second book, which I will also give you a copy of it later on. Thank you very much. We'll see you in the second lecture later on this week.